Here are a couple of photos of balanced rock from a recent trip to Arches. Let's deepen our understanding of what it means to be balanced. We will start with defining some components and later add in the mathematics. First, context. Gravity defying is a phrase that might come to mind when looking at these pictures, so let's roll with that idea and think of this rock in a gravity field. How does gravity affect this rock? Two things we'll consider: mass and first moments. But first, let's simplify. We'll discuss a flat plate or lamina to get a two-dimensional version, and then step that up to 3 dimensions and talk about solids. If we are on planet Earth, we can associate mass with weight, but to be more accurate and to make it easier to generalize later on, we can think of mass as density multiplied by volume. If the density of the object is constant, then this computation to get mass is easy. But if the object has a variable density, meaning the density changes from one area of the object to another, then we employ integral calculus to compute the mass. We'll think of chopping the object up into tiny chunks of volume and assume a constant density for each chunk, compute the mass of each chunk, and then add up all the masses. For a two-dimensional plate, given a density function that returns the density at the point xy, we can compute the mass by integrating the product of density and area. If in 3 dimensions, we compute the mass by integrating the density over volume. Now that we can compute the mass of an object, we are ready to start thinking about balance. To help us understand balance, we are going to define something called a first moment. We can think of a first moment as the tendency of an object to rotate about an axis. For our first encounter with first moments, let's work with a two-dimensional case and study a lamina or flat plate represented by the green object in the video. First, let's see how this object would react to gravity if the object were fixed in place along the x-axis. And then we do the same thing, but fix the object along the y-axis. These videos give us a sense of the tendency of the plate to rotate about a given axis. The first moment about the y-axis is computed with the double integral of x times the density at the point xy over the area of the region. Why does the first moment about the y-axis depend on x and density? Think of x as giving us the distance from the y-axis, and then the density at that point translates into an idea of how much gravity is going to pull down on the object. For example, if the density is low at a point far away from the y-axis, the effect of gravity could be just as strong as it would be for a point much closer to the y-axis, but with a larger density. The integral is a way of averaging this pull over all the points in the green region, and will tell us how likely the object is to rotate about the y-axis. Likewise, the first moment about the x-axis depends on y and the density, and is given by the formula double integral of y times density dA. Incidentally, a question I had was that if there is a first moment, isn't there also a second moment? The answer is yes, and the second moment is also called the moment of inertia, but this video isn't going into that. Let's level up and think about an object more complex than a flat plate. So here are the formulae for computing the first moments for a 3-dimensional solid. Instead of discussing moments about an axis, we talk about moments about a plane. Thus, the first moment about the yz plane is given by the triple integral of x times the density at the point xyz with respect to the volume of the solid region dv. And the first moment about the xz plane is given by the integral of y times the density dv. Finally, the first moment about the xy plane is given by the integral of z times the density dv. Now it is time to consolidate all the information from the first moments to find the center of mass. We will use the known moments and mass to identify the xy or xyz coordinates in the plate or solid that is known as the center of mass. At this point, the object has no tendency to move or rotate and is balanced. For the 2D case, the center of mass is x-coordinate given by the moment about the y-axis divided by the total mass. The y-coordinate is the moment about the x-axis divided by the total mass. We will use x bar and y bar to denote these coordinates for the center of mass. For the 3D case, x bar, the x-coordinate of the center of mass, is the first moment about the yz plane divided by the mass. Y bar is the first moment about the xz plane divided by the mass, and finally z bar is the first moment about the xy plane divided by the mass. Fun fact, if the density of the plate or 3D object is constant, we call the center of mass the centroid.